Hey guys, back with another video here. This is Jake from Jake's Math Lessons TV. Got another problem here today that I'm going to be showing you guys how to work through. Today I'm going to be touching on related rates problems, and in fact, planning on making the next few videos that I post about different related rates problems, kind of going through different geometric shapes and kind of different things to think about there. So today we're going to be going through this problem here. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So real quick, just kind of what makes a problem a related rates problem is, you're kind of thinking about how different measurements or values are changing through time and how they are changing in relation to each other. So basically we're given information about how quickly this radius is changing, and it's asking us to use that to figure out how quickly the volume is changing. So that's kind of where the related rates comes in and kind of what makes a related rates problem. But specifically in this problem, just gonna kind of work through that. So in general, and you'll see me, I'll put links in the description here to go check out my website. I have a bunch of different related rates problems there that I've kind of worked through and explained step by step. So you should definitely go check those out. But you'll see me kind of use the same general process when trying to solve a related rates problem. And that process is to follow these 4 steps here. So the first thing that we always want to do is kind of draw out what we're dealing with. So just basically take in the words that the problem gives us and visualize that by drawing a picture. Usually kind of helps to be able to visualize what's going on here. Then at that point you want to come up with some sort of equation that relates different quantities, distances, measurements, basically just physical measurements that we can measure or imagine that we're measuring in this scenario. And then the third step would be the implicit differentiation. So that is where we're going to take the derivative of our equation with respect to time, and that's where our different rates are going to come from there. And then once you've done that, that's going to introduce the different rates and rate of changes, and then you want to, from there, fourth step is obviously just going to be solve for the rate of change that the question asks you about. So let's go ahead and get started with the first step here, which is to draw a sketch of what's going on. So first of all, the question does tell us that we are dealing with a sphere, right? It says that that's what we're going to be dealing with. So just kind of starting out with the sphere here. Then it tells us that the radius of the sphere is increasing at a rate of 4 millimeters per second. So you could imagine here, the sphere is going to be growing, right? Each edge is going to be moving outward. And the radius, which you can see measured here, is is growing by 4 millimeters each second. And then the other piece of information, or I guess the last sentence, it says, what rate is the volume changing when the diameter is 80 millimeters? So we know the kind of instant we care about. So obviously this sphere is going to be growing throughout time. But the one instant we're looking at is when the diameter is 80 millimeters. So when that is the case, how quickly is our volume changing? So that dV dt over there, there's not really a way to represent that in our drawing. I just kind of wrote it off to the side to remember that, that's what the question's asking us to find. So that dV dt is just saying the rate of change of the volume, which is the V, in relation to time, which is where that t comes from. So now that we have our sketch, we want to come up with our equation. So when we're doing this, there's a couple things I like to think about. The first being, what are we looking for? What is our question asking us to find? So if we look back at our question, you can pretty clearly see the question is asking us how fast is the volume increasing, right? So we need to find the rate of change of the volume. How fast is something changing is basically just saying what's the rate of change of that thing. So if we're looking for the rate of change of the volume, like I kind of said a second ago, typically how we would represent that is dV dt. This is just saying the rate that the volume is changing in with respect to time. So time is our variable, v is kind of what we're measuring, how quickly it's changing. So since dV dt is what we're looking for, we don't necessarily want to put a dV dt in our equation, but we just want to keep in mind that that's what we're looking for. Remember I said our equation needs to be just measurements and distances, that kind of stuff. So not really rates of change. But we're eventually going to take the derivative, which will introduce those rates of change. But what that tells us is that we need to make sure that our equation has a v in it. Because if we put a v in our equation, once we take the derivative, that's going to get us to our dV dt that we're looking for. So thinking about what you're looking for and how to get to that is what you want to consider here. So we need to put a v in our equation, so we know that. The other thing we want to think about is what values do we actually know something about. So clearly it's telling us that the radius is increasing at this rate. So it's telling us about the rate of change of the radius. So we can imagine that as like dr dt, right? So that's just how quickly the radius is changing. So again, we don't want to put rates of change in our equation, but what this tells us is it's okay if we, it's okay if we put r in our equation, because if we have an r, once we take the derivative, we're going to get a dr dt, and we actually know something about the dr dt, so it's okay to use that r in there. And then the other thing that we do know is it's asking us the specific instant when the diameter is 80 millimeters, right? So we know the diameter. If we know the diameter at this instant, remember a diameter and a radius are very closely related, that the diameter will always be just double of whatever the radius is. So if we know about the diameter, then we can also figure something out about the radius. So it's okay to include either of these in our equation. We know about both of those things, and we also know that it's okay to include r, because then we're going to be dealing with dr dt. So this kind of tells us we know everything we need to know about r and its rate of change. So now we need to kind of put that all together. So what we want to think about here are the things that we know and the things that we're looking for. So we know about the diameter, like I just said a second ago, and as a result of knowing the diameter, we also know about the radius. So we could use either of these, whichever one is kind of easier would be fine. And again, since we know dr dt, that's going to tell us that we probably want to include the radius rather than the diameter, because we already know about the radius's rate of change. So that's probably going to be what we want to go with here is the radius rather than the diameter, just because we already know dr dt. And then lastly, we are looking to find dV dt, which means we have to put a v in our equation. We need that. It's not really, like it's okay if we put it in there. We actually need it, because if we don't put a v in there, we're never going to get a dV dt, which is what we're looking for. So really what we want to think about now is when we're dealing with a sphere, we know we need to have a v. It's okay to put an r or a d, but it's probably better to go with r. So we want some equation that relates the volume of a sphere with its radius. First thing that comes to mind when I think about a radius and a volume of a sphere is just the equation for the volume of a sphere, right? Which is this right here. So we know if we have a sphere, this is how its volume and its radius are going to be related. The volume is just 4/3 times pi times the radius cubed. And this is a perfectly good equation to use, because we have our v that we know we need. And then the only other variable in there is r, which we know everything we need to know about r. We know about r, we know about r's rate of change, so that works perfectly. So from here, we'll just kind of proceed with this equation. Real quick, I do want to point out, This equation, again, just contains measurements and distances, basically. So the radius is just some measurement from the center of the sphere to the edge of the sphere, and the volume is some three-dimensional volume that is basically the size of the sphere. So those are just kind of two different measurements. We don't have any rates of change in there. But that's fine because our third step is the implicit differentiation, which is where we introduce our rates of change. So really all we need to do now that we have our equation is take the derivative of both sides. But remember, we do want to take the derivative of both sides with respect to time. So what that means is both of these variables here, v and r, those need to be treated as functions of time rather than variables. So I'll just kind of write here, we are going to be taking the derivative of all of this with respect to time. Right? So time is our variable, v and r are functions of time. Therefore, when we take the derivative of v or r, we're going to need to use the chain rule, because we aren't just taking the derivative of some variable, we're actually taking the derivative of some function of time. So v and r are both functions of time here. So that's what we need to consider here. So now proceeding, pretty much we just need to take the derivative of each of these pieces with respect to time. So when we take the derivative of v with respect to time, like I just said, v is a function of time, but we don't really have an explicit formula for v with respect to time, so therefore we can't really know an explicit derivative for v with just t being our variable. So really the best we can do is just to say that the derivative of v is just dv dt, which literally just means the derivative of v with respect to time. So then, kind of similar on the right side of our equation, we have some function of r, which r is actually a function of time. So when we take the derivative over there, we're going to need to use the chain rule again. So kind of considering this as the chain rule, we're going to need to take the derivative of the outside, leave the inside alone, and then multiply that by the derivative of the inside. So keep in mind this 4/3 pi that's in front of our r cubed is just a constant coefficient. Pi is just some number. 4/3 is just some number. 4/3 pi is just a constant. So that's pretty much just going to carry through into our derivative. Because the derivative of some constant times our variable, that constant can just stay in front and kind of carry through like that. So now when we're taking the derivative of r cubed, that's where kind of the chain rule is going to come into play. So first we can just do power rule, right? So move the 3 down in front, lower the power by 1. So 3 minus 1 is 2. So we have 3r squared. Now we need to multiply that by the derivative of the inside. Our inside is just that r, which, just like when we took the derivative of v, we don't really know what r is in terms of time. So to take the derivative of r, really the best we can do is just say the derivative of r is just dr dt, because since we don't have an explicit function for r, we can't really have an explicit function for the derivative of r. Therefore, multiplying by the derivative of r inside is just times dr dt. Right, so this 3r squared dr dt, that's the derivative of the r cubed piece, right? So now we can kind of put that back in our other equation over here. We can kind of just drag that over. So that 3r squared dr dt is the derivative of r cubed. So we can kind of just place that over there in our derivative. And remember, it's just being multiplied by that constant 4/3 pi over there. So now we can pretty much just simplify this a bit here. dv dt, obviously not much we can do there. Just carry that down to the next step. Now notice these 3's will cancel out because we're dividing by 3 and then multiplying by 3. So those will just cancel, which will just leave us with 4 pi times r squared times dr dt. And that is our derivative of both sides of that equation that we originally had up there. So that was, remember, the derivative of that v equals 4/3 pi r cubed with respect to time gives us dv dt equals 4 pi r squared times dr dt. So that is really all there is to the implicit differentiation step. So now, really all there is left to do, we can go ahead and move on to our fourth and final step, which is to solve for, our desired rate of change. Solve for the rate of change that we were looking for. So to do that, we'll just kind of grab this equation that we just found a second ago. Now remember back a couple steps ago we figured out that what we were looking for was dv dt. So the first thing you want to do when you're solving for the desired rate of change is just to isolate the variable that you're looking for. In this case, it's already isolated, right? Because we're looking for dv dt, which is already all by itself over there. So really all there is left to do at that point is just to plug all the other values that we know, just plug those into our equation here, and that should give us our answer. So we're going to need to plug in what r is at the moment when we are looking at here, and we're going to need to plug in what dr dt is at the moment that we're looking for. So we know that the diameter of the sphere at this moment was 80 millimeters, right? The diameter of a sphere is always going to be double the radius. So if the diameter is 80, the radius would obviously just be 40 millimeters. So we're going to plug in 40 for r. And then if you remember, look back at the original equation, it was saying that the radius of the sphere is increasing at a rate of 4 millimeters per second. So our radius is changing at that rate of 4 millimeters per second. Therefore, dr dt basically just represents the rate of change of the radius, how quickly the radius is changing. Since it's increasing at 4 millimeters per second, that dr dt value is just going to be 4. It's going to be positive because it is increasing, so therefore it's going to be positive 4. So now we just need to take this r and this dr dt and just plug those in, and that should give us what we want. So if we go ahead and do that, that'll tell us that dv dt is just 4 pi times r, which is 4, squared. Sorry, r, which is 40, squared. And then multiplied by our dr dt, which is just times 4. So this should give us the rate of change of the volume with respect to time at this moment when the radius is 40. So now, just to simplify that, if we plug all this into a calculator, we will figure out that dv dt would equal 25,600 pi. And we could multiply that pi out, give us some approximation, which is about 80,424.772. And that's just going to be millimeters per second. Sorry, millimeters cubed per second. That's just going to be millimeters cubed per second, because the unit that we were using to measure our distance was millimeters, and our unit to measure time was seconds. Volume is a three-dimensional measurement, right? So we're going to need millimeters cubed to measure our volume. So this is going to be changing at a rate of cubic millimeters per second. So that's it. That gives us our answer. That tells us, how quickly the volume is changing with respect to time when the diameter of our sphere is 80 millimeters. It's just going to be that 25,600 pi cubic millimeters per second. That's all it takes. So like I said, I have a page on my site where I kind of work through this problem step by step. If you want to go check that out, if you're seeing this somewhere else, definitely go check it out. I'll put a link in the description below. If you are watching this on my site, well then thanks for coming, and hope to see you back here soon. Like I said, kind of at the beginning of the video, next few videos I post are all going to be related rates problems and work-throughs. So if you are trying to learn and get some practice doing related rates, check back for more. If you are on my YouTube channel, Jake's Math Lessons, go ahead and subscribe, and you'll be notified whenever I post some new videos, so you can keep checking those out, and hopefully those will help you solve these related rates problems. But really the process is going to be pretty similar every time. We're going to go through these 4 steps, and really that should get you to the answer that you want every time. So thanks for watching. Hope to see you back soon, and more to come shortly. Thanks.